Today we're going to look at the laws of exponents. So first, let's remind ourselves what an exponent is. An exponent is a number that some other value is raised to. For example, in what I've just written down, the exponent is 2. Now, what the exponent means is that you're multiplying the value by itself that number of times. So x raised to the power of 2, or x squared as we might say, is simply x times x. X raised to the 4th power is simply x times x times x times x. It's x multiplied by itself 4 times. This also works with standard values. For example, 3 to the 2nd power is simply 3 times 3, which becomes 9. So let's start off by looking at the power of 1. The power of 1 simply states that any value raised to the power of 1 is simply equal to that value. X raised to the 1st power is equal to x. 9 raised to the 1st power is equal to 9. This works because every value has an unwritten exponent. If you were to write the expression x plus 3, you're really saying that it's the same as x plus 3, where x and 3 are both raised to the 1st power. This is the simplest of the laws. Now let's look at the power of 0. The power of 0 states that any value raised to the power of 0 is equal to 1. And this holds true for any value whatsoever. For example, 6 raised to the power of 0 is still equal to 1. X times y raised to the power of 0 is also equal to 1. The expression 3x plus 5 raised to the power of 0 is still equal to 1. No matter what happens, any value raised to the power of 0 is equal to 1. The proof of this comes from dividing with exponents, which we'll talk about in a little bit. But just to show it to you, x squared divided by x squared is the same thing as x to the 2 minus 2, which means it's x to the 0. We also know that x squared divided by x squared has to be equal to 1, because any value, such as x squared, divided by itself is equal to 1. Therefore, x to the 0 power must be equal to 1 as well. Now let's look at negative exponents. The law of negative exponents states that any value raised to a negative exponent is equal to 1 divided by x to that value. You'll notice two things have happened. First, the x has moved to the bottom of a fraction. That is to say, we've inverted it and found the inverse of x raised to the n. You'll also notice that the value of the exponent has gone from negative to positive. For example, 4 to the negative 1 power will be equal to 1 divided by 4 to the 1st. We know from the power of 1 that 4 to the 1st is 4, so this is simply equal to 1/4. X raised to the power of negative 3 can be rewritten as 1 divided by x to the 3rd. In this case, since we don't know what x is, we'll leave it as 1 divided by x to the 3rd. 3 to the negative 2nd power would be rewritten as 1 divided by 3 squared. Since we know that what squared means is that it's 3 times 3, that simply is 1 divided by 9. Now something interesting happens when we look at two new examples. The examples are 2 times x to the negative 2 and 2x to the negative 2. In the first example, the variable x has the exponent negative 2. In the second example, the entire phrase 2x is raised to the negative 2 power. What's important about this is to realize that in the first case, the exponent only applies to the x, while in the second case, the exponent applies to everything. Therefore, this first expression becomes 2 times 1 divided by x squared, while the second expression becomes 1 divided by 2x squared. For the first expression, if you multiply it out, you'll get 2 over x squared. The bottom expression is already complete, but we could multiply it out and have 1 over 2x times 2x, which simplifies to 1 divided by 4x squared. What this is showing you is that the placement of the exponent is extremely important to how we work through these problems. Next, let's look at factors with exponents, or multiplication. Factors with exponents is what happens when we talk about multiplying two values that have exponents. In this case, x to the m power times x to the n power can be represented as x to the m plus n power. This only works when our base is the same. The value of the base must be the same. Whether it's x or 3 or 12, it has to be the same value raised to a power to be able to multiply them together. So, for example, x to the second times x to the third would become x to the 2 plus 3, or x to the fifth. In order to show how this works, let's look at a proof. X squared times x to the third could be rewritten as x times x times x times x times x. In this case, x squared was rewritten as x times x, and x to the third was rewritten as x times x times x. As we work through this, we know that we have 5 values of x that are each raised to the first power. As a result, it shows that these are equal to x to the fifth. So let's look at a couple more examples. Three to the second times 3 to the third would be 3 to the 2 plus 3, or 3 to the fifth power. To check our work, we can use a calculator to show that 3 to the fifth power is 243. To check it, let's look at these equations. 3 squared is 9, 3 cubed is 27, which is also equal to 243. So once again, this shows that we can add our exponents so long as our base, in this problem the base was 3, are the same. Y to the 6th times y to the 9th simply becomes y to the 6 plus 9, or y to the 15th. Once again, since we don't know what y is, that's already in simplest form. Since we've looked at multiplication, let's look at division next. Division with exponents follows the following law. X to the m power divided by x to the n power is equal to x to the m minus n power. You'll notice that this is the opposite of our multiplication. In multiplication, we added the exponents. With division, we are subtracting. Once again, our bases, in this case x, must be the same. So once again, let's take an example. X to the 6th divided by x squared would become x to the 6 minus 2, or x to the 4th. To look at a proof, we'll examine this problem in a different way. X to the 6th over x squared could be rewritten as x multiplied by itself 6 times, divided by x times x. Since we know that a number divided by itself is 1, we know that x divided by x becomes 1, and the other x divided by x becomes 1. Our final result is simply x times x times x times x, or x to the 4th power. So let's look at a couple examples. 3 to the 6th divided by 3 squared would become 3 to the 4th, or 81. To double check this, we know that 3 to the 6th divided by 3 squared is also equivalent to 729, which is 3 to the 6th, divided by 9, which is 3 squared. This also comes out to 81, so we know we've done things correctly. Now let's look at power to a power. The law for power to a power states that x raised to the m power, which is in turn raised to the n power, must be equal to x to the m power times the n power. So in this case, we are multiplying our exponents together when we once again have the same base of x. For example, x squared to the 3rd is equal to x to the 2 times 3, or x to the 6th power. To look at a proof, we'll once again rewrite it in a different way. X squared to the 3rd power is really saying that you're multiplying x squared by itself 3 times. X squared can be rewritten as x times x. So if we rewrite it a second time, we're showing that we have 6 x's, or x to the 6th. Let's double check this with an example. 3 squared to the 3rd power can be rewritten as 3 to the 2 times 3. In this case, on the left-hand side, 3 squared becomes 9 raised to the 3rd power, while on the right-hand side, we have 3 to the 6th. 9 raised to the 3rd power is 729, and 3 to the 6th is also 729. So we've shown that these two are equivalent. Next, we'll look at distributing exponents. Distributing exponents follows the following pattern. X times y to the n power is equal to x to the n power times y, also to the n power. This also works for division. X divided by y to the n power is equal to x to the n power divided by y to the n power. In this case, we've distributed the value to each of the factors inside the parentheses. For example, xy to the 3rd power is equal to x to the third times y to the third as well. Let's prove it. xy to the third can be rewritten as x times y times x times y times x times y. A little bit of rearranging shows us that x times x times x times y times y times y is the same as the previous statement. We once again have 3 x's and 3 y's, so we can rewrite this as x to the third y to the third, or x cubed y cubed. So let's look at a couple of examples. X over y squared is x divided by y times x divided by y. We know from our fraction multiplication that we'll multiply straight across for both of these. So our final result is x times x, which is x squared, over y times y, which is y squared. So let's look at a numerical example. We can work this out in two ways. On the left, we'll do 6 divided by 3 times 6 divided by 3, simply rewriting this without an exponent. On the right, we can work it out by doing the actual division, 6 divided by 3, which gives us 2 squared. On the left-hand side, 6 times 6 is 36, 3 times 3 is 9, and on the right side we still have 2 squared. 36 divided by 9 is 4, and 2 squared is also 4. So once again, we've shown that this works. Finally, we're going to look at fractional exponents. Fractional exponents are exactly that. A value where the exponent is actually a fraction. In this case, x to the m divided by n can be rewritten in two different ways. We could rewrite it as n or the nth root of x raised to the m power. Or we can also rewrite it as the nth root of x raised to the m power. Fractional exponents are extremely important later on when we're converting square roots and exponents in between each other. For the most part, we won't use them very often in this class, but I want you to be familiar with what it looks like. The most important thing to think about is simply that x raised to the 1/2 is the same as the first root of x whoops, I got that one wrong. I'm sorry, x to the 1/2 is the same thing as the second root of x, or the square root of x. So just remember that anything raised to the 1/2 is the same thing as having the square root of that value. That's it for laws of exponents. So we'll look at some more things to do with this next time.